So let's do some problems from Chapter 7 now. Remember in Chapter 7 we talked about the second law of thermodynamics and how there are limits to how efficient our heat engines or refrigerators can be, because we always have to reject a certain amount of heat to a sink or our surroundings, right? Especially if we're talking about a heat engine here. So an example of that is given here in this first problem, where we have a hot temperature source, something that's hot, providing our heat engine with 700 kilojoules of heat. Our output work is 250 kilojoules, and we have to reject some amount of heat for this process to be possible. All right? So the amount of heat that we would need to reject for this process to be possible would be what? Well, in order to calculate this is just a very simple calculation. The energy that's coming into our heat engine is 700 kilojoules. The energy leaving our heat engine, so this is what's coming in, so in. What's coming out of our heat engine, remember, we have to apply the first law of thermodynamics also, which says energy is conserved, where we have 250 kilojoules coming out as work, plus QL. So, solving for QL, we get 450 kilojoules. So, we would have to reject or lose 450 kilojoules of heat for this process to be possible. And we'll get into some Carnot heat engine examples later, but for now, this is just a heat engine example illustrating the point that we do in fact need to lose some heat energy for our cycle to be completed. Now this one's a little bit different. Let's take a look at it. We have a hot temperature source. So we're going to say this hot temperature source is a coal power plant. And the coal power plant consumes 60 tons per hour of coal. And the coal has a heating value or an energy amount in it of 30,000 kilojoules per kilogram. So if you burn 1 kilogram of coal, you would get 30,000 kilojoules of energy out of it. Now the question of this, if we are able to do this cycle or have this system and output 150 megawatts, the question is, what is the thermal efficiency of this system? So using the definition of thermal efficiency in your text, we're just going to say that thermal efficiency is the work output of this heat engine, which is our power plant, divided by QH. So that's just the basic definition of what our heat engine is, okay? So the work out, that's the basic definition of efficiency, the thermal efficiency of our heat engine. So the work output, this is going to be 150 megawatts divided by QH. So we need to find QH in order to be able to solve this problem. Well, QH here is going to be found using this consumption of fuel by our system. So we're consuming 60 tons, okay? And I'm going to say this is metric tons, okay? Make our life a lot easier. So 60 metric tons, that means 60,000 kilograms. So let's go ahead and write that. 60,000 kilograms per hour. Okay. And let's go ahead and convert that hour to seconds just to make our lives easy again. So 1 hour has 3,600 seconds. Okay. And also we will use our heating value, our energy storage of our fuel, which is 30 megawatts per kilogram. Now notice I converted 30,000 kilojoules. I'm sorry, this should be 30 kilojoules per kilogram, not megawatts. I'm thinking one step ahead, I think, here. 30 kilojoules. So I've divided this kilojoules per kilogram by 1,000. Oh, once again, I have megajoules per kilogram. Okay. We should be okay now. So let's look at our units. Kilograms, cancel. Hours, cancel. And our value that we obtain here is 500 megawatts. So our heat input into our heat engine is 500 megawatts, and of the 500 megawatts, we're able to only extract 150 of those, and we have to reject the rest of those to a cold source in order for this cycle to be possible. All right, so let's determine the thermal efficiency now. So our thermal efficiency, I'll just write it again down here, is equal to 150 megawatts divided by 500 megawatts. That gives us a thermal efficiency of 30%. Okay, so we're just using the second law of thermodynamics and some of the principles we learned, like the Kelvin-Planck statement, in order to prove that some of these cycles exist and how we would calculate those. So let me just work out one more problem for you guys here regarding this topic. In the next video, we'll talk about Carnot heat engines, and we'll also talk about Carnot refrigeration cycles. But here's a refrigeration cycle, not necessarily a Carnot cycle, okay? And in this cycle, we have a coefficient of performance of 1.2. We have a work input that we don't know. We have a QL of 60 kilojoules per minute. So we're extracting heat out of the cold environment, so out of our refrigerator. The question that we want to determine is what is the work needed in, what is work in, and what is work in, and what is QH. So those are the questions we are asking for this problem. So I'm just going to use the coefficient of performance definition from our textbook. So the coefficient of performance for refrigeration cycle is going to be QL by definition over work in. Now the coefficient of performance for this refrigeration cycle is already known, so this is 1.2. QL is 60 kilojoules per minute. And work in is one thing that we're trying to find. So solving for work in, we can show that work in is equal to 833 watts. I may have skipped a step here. Just, I didn't show it, but you can convert this, 60 kilojoules per minute into watts. So 60 kilojoules per minute, and there's 60 seconds every minute. So the minutes cancel, so you have kilojoules per second. So this is basically 1 divided by 1.2, okay? So that's where this number comes from. Now the next thing we'd like to find is the heat that's rejected to to the heated environment from our refrigerator. So again, we'll use the definition of the coefficient of performance from our textbook of 1 over QH divided by QL minus 1. And we've already established that the coefficient of performance is 1.2. We also know that QL is given, so we can say this is 1 over QH divided by 60 kilojoules per minute minus 1, and all of this is equal to 1.2. So you guys can solve for QH in this. I'll leave the algebra to you, but QH should come out to be 110 kilojoules per minute. Okay, so those are a few examples of the application of the second law of thermodynamics. What we'll talk about next time is we're going to talk about the different Carnot heat engine and Carnot refrigeration cycles and work out some problems for that type of system.